every single derivative trick which I figure out how to visualize, visualized. Take a square of side length x, then nudge x by a small amount dx. What's then the change in the area? You can see it's composed of two of these rectangles and one tiny square, which we can effectively ignore. That's negligible. So we have two x by dx rectangles. So if we change it by some small amount dx, the area will change by 2x times that. We can do the same thing for a function like x cubed. Say we have a cube of side length x, then nudge x by some small amount dx, and see what the change in the volume is. Well, it's 3 very thin plates plus 3 very thin strips plus 1 really tiny cube. We can ignore all the strips in the cube and just focus on the plates because they're tiny in comparison. So the area is going to be 3 x by dx plates. Dividing through by dx like we did before gives us 3x squared. The sum rule is actually kind of simple. It doesn't really need any trickery. It's just to find the derivative of the sum of two functions. That's just the sum of the two derivatives. We can use this to figure out polynomial derivatives, by the way. We just break them up into their individual components, which are all x squared, x cubed, and so on. And then we just find the derivative that way. Now let's say we want to figure out the derivative of one function times the other. This one is a little more complicated. Let's say we have a rectangle with one side length being f of x and the other side length being g of x. Let's say we nudge x by some small amount dx, then the f of x side will be nudged by some amount df, and g of x will be nudged by some amount dg. Again, the square at the top right is negligible, and we're just left with a df by g of x rectangle and a dg by f of x rectangle. We can divide through by dx, and we get that the derivative is the derivative of f times g plus the derivative of g times f. That's the derivative of f times g. Sadly, it's not the derivative of f times the derivative of g. That's a common mistake. But yeah, the problem rule that says that it's not. So we want to figure out the derivative of sine. Warning, this one will be a little less thorough because I haven't really found a good visualization trick for it, but it doesn't really... but at least gives some intuition. Okay, first question. When is the derivative 0? Well, the answer is when the function is completely flat. That's every pi points. Here's the second question. Where is the derivative the highest? Well, that's then when the sine function is the steepest going up and to the right. So that's the blue points. And where the derivative is lowest is the red points. We can use this to get a rough sketch of the derivative of sine of x. This looks a lot like cosine of x. And in fact, that's correct. We can use the same exact method to figure out that the derivative of cosine is negative sine, and the derivative of tangent is a function called secant squared. It's a little bit more obscure, but yeah, So we want to figure out the derivative of f of g of x. So the derivative of the two functions smooshed together, otherwise known as composed together. So we have 3 number lines visualizing x, what happens when we apply g to that, and what happens when we apply f to that. And we're gonna mark x on the first number line, g of x on the second number line, and f of x on the third number line. Let's say we nudge x by some small amount dx. That nudges g of x by some small amount we'll call dg, and that in turn nudges f of g of x by some small amount we'll call df. Now, per the definition of derivatives, df is equal to the derivative of f at the point where we call it, which is g of x, warning there, multiplied by dg. We can use the same thing to figure out that dg is the derivative of g times dx. Combining those two, we get that df equals the derivative of f at g of x times the derivative of g at x times dx. If we divide through by dx, we get the derivative, which is the derivative of f at g of x times the derivative of g at x. Whew. That's all. There are more derivative tricks out there, but I haven't really found a good way to visualize them all. Hope you guys enjoyed the video, and bye there.